Hello everyone, my name is Jack Becker, and this is the first video lecture in my Calc 1 series. So, a little bit about me. I am a first year double major in mechanical engineering and physics at North Dakota State University. I just finished my first semester, took Calc 1 with Professor Jason Boyden. If you're going to take Math 165 in the fall, I highly recommend him. He is probably the best math professor I've ever had. But a struggle that I found was that the teaching style, I guess, of them was not really for me, or like it was very hard to understand. So what I'm going to do throughout this series is go through each lecture and like simplify it so it's like very easy to understand. So yeah, so now let's talk about lines, specifically secant versus tangent. So a secant line connects 2 points on the curve. It tells you the average rate of change over an interval. And then a tangent line touches the curve at one point. It tells you the instantaneous rate of change at that exact y value. So in summary, a secant slope is equal to the average change. And a tangent slope is equal to the instantaneous change. So you want to think of slope as the rate of change in a graph. That is how you're going to make sense of all of this information. So now we have the core concept of average rate of change. So we have 2 points, x equals a and x equals b, on a graph, right? So the formula to do this is f of x is equal to f of b minus f of a over the original points of b minus a. So this is literally the change in input over the change, or it's the change in output over the change in input. So geometrically speaking, it's a slope of a secant line, right? So imagine we have a secant line at the points a, function of a, and b with a function of b. This is the full concept of average rate of change. This is my understanding of it, and that is the most simple it can be done. So now we have an example of average rate of change. So we want to find the average rate of change of the function or the polynomial 2x squared minus 3x plus 1 on the interval 1, 4. So remember our equation is f of b minus f of a over b minus a, right? This is our equation. So what we want to do is basically plug in the different values of our equation, right? So we have f of 4, which is equal 2 times 4 squared minus 3, 4 plus 1, and that is 2 times 16 minus 12 plus 1 equals 32 minus 12 plus 1 equals 21. So this is our answer for f of 4. And now we want to plug in f of 1. So that's 2 times 1 squared minus 3 times 1 plus 1 equals 2 minus 3, I'm pretty sure. equals 0. So now, and then we want to use our f of b minus f of a over b minus a, right? So this would equal 21 minus 0 over 4 minus 1. And then that would equal 21 over 3, which would equal to 7. And that is our final answer. So now we have an application problem involving average rate of change. So we have a runner's distance from the start in meters after t seconds is this function right here. We want to find the average velocity on the interval 2 to 6. Okay, so we want to think about it in the f of b minus f of a, blah, blah, same thing. So the average velocity is the average rate of change of position, right? So we want to think about it as a s of 6, right, minus s of 2, I believe, over 6 minus 2. We want to think of it as this equation right here. So we first want to plug in s of 6, right? So we have 6 squared plus 2 times 6 equals 36 plus 12, which equals 48. And then it's s of 2 equals 2 squared plus 2 times 2 equals 4 plus 4, which would equal 8. So now we want to plug these values back into this equation. So now we have 48 minus 8 over 6 minus 2, which equals 40 divided by 4, which would equal 10. And that is our final answer on how to solve an application problem. So now we're getting to the core component of all, instantaneous rate of change. So think of instantaneous rate of change at x equals a is what happens when the second point moves closer and closer to a. So we let b equal a plus h, where h right here is a small change in x. Then we shrink h to 0. So we have the IRC, right? So I'm just gonna call it IRC, short for instantaneous range. So is equal to the limit as h approaches 0, right? This is important, of f of a plus h minus f of a over h. This is a core formula in calculus because geometrically the secant line becomes the tangent line, which means the limit, so the limit is the derivative of f prime of a. This formula is a core piece for derivatives, which we will touch after this entire limits unit. Derivatives, in my opinion, are pretty unique and they're pretty cool. I personally really liked integrals, but derivatives are the stepping stone to integrals. So now we have an example using the limit definition. So we have a function. We want to let the function of x equal x cubed minus 4x plus 1. And we want to find the instantaneous rate of change at x equals 2 using the limit definition. So here is basically our equation, or the thing we want to use. So, and then we'll get to the work right now. Okay, so you want to start off by plugging in the values, right, into the equation, whatever, and for the 2 plus h, I end up getting 1 plus 8h plus 6h squared plus h cubed. You can FOIL it out all yourself if you want to figure out how I got there, but just save time, I did that. So now we want to plug it back. So now we want to plug into our equation, right? So we have 1 plus 8h plus 6h squared plus h cubed minus 1 over h, right? Which would equal 8h plus 6h cubed plus h cubed over h. But since we're approaching 0, all the 8, or you can set, so the h's would cancel, right? So all the h's in the equation would cancel, so you're just left with 8 plus 6h plus h squared. So as the limit, so now we're left with the limit as h approaches 0 of our new equation, which is 8 plus 6h plus h squared. It simply becomes 8. And that is how you solve a instantaneous rate of change problem. So the last key concept I'm going to go over in this video is the difference quotient, which is a really important expression. So the slope of secant line from x to a plus h. So if h was a normal number, it will give the average rate of change. So this, by definition, is the average rate of change. But if you take the limit as h approaches 0, it becomes the instantaneous rate of change. So by definition, this is the IRC. It is important to know, well, a thing that I really struggle with is you can't automatically plug in h equals 0, because it would become 0 over 0, which is equal d/e, or by NDC's definition, undefined. And that is not good. So you want to simplify the expression first and then plug it in. So that is the basics of limits for average rate of change. I hope you guys enjoyed this video, and I hope it somewhat helped. If it didn't, that's okay. Leave me some comments, and I will try my best to improve it. So, yeah. If you're just starting out with Calc 2 or Calc 1, it's going to be hard, but the more work you put in, the better it's going to be, and it gets easier. So, I wish you all good luck, and have a great rest of your guys' day.